But first I want to talk about rotation curves. What is a rotation curve? Is a graph of distance versus orbital speed. Although actually I said that backwards. Usually it's plotted orbital speed versus distance. So what do we mean by orbital speed? Well, it's easy to think about the solar system because that's something where we're familiar with orbits in. Here's the Earth. It's whipping around the sun pretty fast. Here's Mars. It's whipping around the sun not as fast. And here's Jupiter. It's whipping around the sun even slower. There's a pretty simple relationship between the speed and the distance from the center of the solar system that an object goes around the center of the solar system, and here it is plotted. So on the horizontal axis we have the distance from the sun in astronomical units, where an astronomical unit is defined as the distance from the Earth to the sun, or about something like 200 million miles. Something like, what is it, 1.5 times 10 to the 11th meters, if I remember correctly. But it doesn't matter. The point is, that's a good distance to measure distances in the solar. Yeah, 8.3 light minutes. And here's the velocity in kilometers per second, which is like kilometers per hour, only 3,600 times faster. So here's the Earth. Earth is going around the sun at about 30 kilometers per second. So hold on to something. Mars slower, Jupiter slower still, and you can see that they fall nicely on this curve. And in fact, what this curve is not just a line connecting the dots. This curve is the theoretical prediction from Kepler's laws, and then the dots are the actual real data, and you can see that, well, okay, we understand the solar system pretty well. Now the solar system, so these are called Keplerian orbits. Why? Because they obey Kepler's laws. Keplerian orbits is, so that's a jargon for orbits that follow this rotation curve. And when do you get this rotation curve? When all of the mass is right at the center, which is very close to true in our solar system. It's not completely true because, of course, the planets have mass, but the mass of the sun is something like 1,000 times the mass of Jupiter. I said that wrong. It's something like 1,000,000 times the mass of Jupiter. No, more like 1,000. I'm sorry. Whatever. It's a few thousand times the mass of Jupiter. I don't remember the exact number, and Jupiter is by far most of the rest of the mass in the solar system. So all except for less than 0.1% of the mass of the solar system is right at the center in the sun. That's right. What's 3 orders of magnitude among friends? Well, if you're in the solar system, it makes a pretty big difference because it means that we're all orbiting around the sun instead of something else. Now, you may remember from last time we're not orbiting exactly around the sun, but we're orbiting very close to around the sun, which is why this Keplerian prediction works so well. So when you have all the mass right at the center, you get Keplerian orbits. Now, that doesn't work for galaxies because you already have seen that galaxies are these big spread out things. So let's think about how are we going to think about rotation curves. So imagine yourself, that's you, all right, you need to put on a little weight, and you've got a rope in your hand and you're swinging a ball around your head. Woo, 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 right? Fun stuff. We've all done this. And if you haven't, I recommend it, but I recommend you go outside first because you might break something. It's Randall Munro, that's exactly right. This is Randall Munro swinging a ball around his head. And if you do this, you will feel the rope kind of pulling on your hand. As it swings around, the ball tries to pull your hand, and so you pull back on the rope. That's Newton's third law, action-reaction. So it is you pulling on the rope that holds the ball in the circle. If you were to cut the rope, the ball would go flying off in this direction. Whee! But instead, because there's this rope pulling on the ball, it holds it in the circle. So it is the force of the rope holding the ball in this circle. Now, here is a question for you. This is the kind of thing I used to do in my classes. I would put this up, and I would ask them a question. In which case will you need to pull harder on the rope to keep the ball moving in a circle? Right? So you're on the left one, you're spinning slower, kind of slowly winging it around. And on the right side, you're really winging that puppy around. All right? On which one do you actually have to, and don't think about difficulty, right? Because, of course, it's going to try and sag a little bit. Think about you're rolling it fast enough so that it holds up. But then do it faster, in which case are you pulling harder on the ball, on the rope. And this is another thing, do try this at home. Go ahead and tie a rock or something at the end of a rope. And I see that we've got sort of a mix of answers here, so I'll go ahead and tell you the answer is spinning faster. Turns out that spinning faster, you need to pull harder on it. And if you don't believe me, go and try it, right? You will find that the faster you spin it, the harder you're pulling on the rope. If you really don't believe me, go ahead and connect a scale somehow with a spring between your hand and the rope, and you'll see that the force gets higher as you're spinning faster. So this is an experiment you can actually do yourself. Right, and so some people are even oh, don't do it with a kitty. That's so sad. Some people are throwing up the equations that are related to this and that sort of thing. But the important point here is that a faster orbit means more force is necessary to keep it in orbit. If you don't hold it, right, and a thread will break if spun too fast. Why? Because eventually you're asking the thread to have more tension than it can hold. Yes, and I recommend not actually making yourself throw up. Unless you like that kind of thing, but that'd be strange. So the important thing here is that the faster the orbit is, the more forces that is needed to keep it in orbit. So let's look at galaxies. Well, all right, first of all, we want to measure the rotation curve, which means we want to plot the velocity that stuff is moving as a function of how far it is from the center of the galaxy. All right, well, how do we measure it? Well, we measure it using the good old-fashioned Doppler shift, which is a nice thing. You may have heard this with sound. If a car goes past you, you'll hear the car make a sound something like this. And what's happening is, as the car is coming towards you, you hear a higher pitch, and when it passes you and is going away, you hear the lower pitch. Well, pitch in sound waves is related to the wavelength of the waves. A higher pitch is a shorter wave. A lower pitch is a longer wave. The same exact thing happens with light. So if you're looking at something and it would have given you light of a certain wavelength, if it's coming towards you, so this is me here, I need a haircut, looking at a star, here, and I need to get something done about that nose too. Here I am looking at a star. If that star is coming towards me, the light I see from it will be blue shifted. It'll be shifted to shorter wavelengths, and shorter wavelength light is bluer. And if the star is moving away from me, the light I see from it will be red shifted. Red shifted light is light with a longer wavelength. Right? And the Doppler shift works like that. So we could do this for stars. We go out and we look at stars in a galaxy. If we measure, say, an atomic transition line for hydrogen, for example, there's a line at 6,563 angstroms. If you're an astronomer, that's 656 nanometers if you're a physicist. Same thing. It's a well-known line of hydrogen, and if you see that line and you see it at a slightly different wavelength, you'll say, aha, it's the Doppler shift. It's because the stars are either moving towards me or away from me. So that's exactly what we do. We go out and we look at these galaxies. I could have sworn I clicked next. I'll click it harder. Uh-oh. My slide projector has stopped listening to me. Oh, there we go. Now it's probably going to jump forward multiple times. Yes. Because I hit it a few times. So let me hang on while I try and get control of my slide projector again. All right. So what we do is, right here, as you look at, yeah, it has been built. This is a galaxy that's tilted, so we're kind of looking down on the top of it. So if it's going around this way, right here, the stars are moving partially away from us. And because they're moving away from us, we'll see a red shift. And over here, they're moving towards us. Because they're moving towards us, we'll see a blue shift. If any of you guys are wearing like a Mista tool or something like that, could you disable it or take it off? Because I think we're starting to get some script lag in here due to the number of people we've got. That's why I was having trouble turning pages. So that's what we do. Now, so that's how we measure the rotation curves from the Doppler shift. So the next thing we want to do is figure out what rotation curve do we expect. If all the mass was right at the center, it would be a Keplerian rotation curve. But we don't expect that because, look, there's stars out here too. And so the way to think about it is for a star at a given distance, so there's a star right here at the center of this circle. What is holding it moving in the circle? It's moving off in some direction. It would go flying off in this direction, except there's stuff holding it in a circular orbit. And because it's in a circular orbit, there must be just the right amount of mass to hold it there. Well, it's all the stuff between here and here is what's holding it into the orbit. It turns out that the stuff out here doesn't really matter. You'd think it would be pulling it away, but by the same token, if you look at the stuff out here that is farther away than the stuff between here, the center, and where its orbit is over here, the stuff out here pulling towards it ends up compensating for the stuff over here. It's not perfect. It turns out it is perfect in a spherically symmetric situation. It's not perfect in a disk galaxy, but it's very close. So for purposes of kind of understanding what's going on, you can think that all the stuff that is closer to the center of the galaxy than the star that's going around, so all the stuff between here and here, and also on the other side, all that stuff, all the stuff within the circle the star is making, that amount of stuff is what is holding the orbit in. So if the orbit is faster at a given distance than you expect, that means there's got to be more matter than you expect. So already you should expect that things that are farther out from the center of the galaxy should be moving faster than is the Keplerian case. Why? Because there's all this extra mass here. In the solar system, all the mass is right here, and this guy would be moving relatively slow. But in the case of something that's distributed like a galaxy, there's more mass. You can see it. Look at it. Look at all those stars. They all have mass. So this thing is going to be moving faster because there's more mass holding it in, and if it's going in a circle, it's going to be a faster circle because there's more mass and there's therefore more gravity. So by looking at all these stars and figuring out how many stars there are and how big they are and looking at all the gas, we can add up the gravitational effect we expect and figure out how fast everything ought to be moving. And that's what I have on the next page. All right. So first of all, here's the Keplerian curve just for comparison. It looked like that before. If we observe the matter in the galaxies, the stars, you actually expect a curve that looks something like the orange curve. And it is. It's going faster than the Keplerian curve because as you go farther out, there's more stuff there. All right. So this is what we expect from all the stars and gas we can see. What we really observe in terms of speeds, though, is this. So there's a gap. If we add up all the stars and gas that we see, there isn't enough gravity to hold the galaxy together. All right? Stars and gas in the outer part of the galaxy are moving too fast. Notice towards the center of the galaxy, if we add up all the stars and gas, we get it either exactly right or pretty close. But as you get further and further out, the discrepancy gets bigger and bigger. So what that's telling us is, it's telling us one of a couple things. Either it's telling us that we don't understand gravity right, and we're getting gravity wrong out here. You know, that was a real possibility that I think we've more or less ruled out now. But okay, that's one possibility. We don't understand gravity right. Second, that was one possibility. The other possibility is that there is more mass in the outer parts of galaxies than what we've accounted for. Stuff we can't see. That we call dark matter. Now, if you remember my talk a couple weeks ago, we saw some of the motions of Uranus's orbit could not be explained by all the stuff we could see, and people used that to predict where Neptune would be. So in this case, we have all this difference, and so we can predict where all this extra mass ought to be, and that's what we call dark matter. It's the stuff that's holding the galaxy together. All these stars moving this fast would go winging off into intergalactic space, except there's enough gravity to hold it together. All right, so when we observe galaxies that have collided, are the orbits red, blue, shift, Keplerian? No. When we looked at collided galaxies, it's a big, huge mess. You have stuff going all over the place. The nice, clean, circular orbits get all screwed up as stuff interacts with each other and gets all stirred up. So you tend to see a nice, huge old mess as galaxies collide with each other, and it's pretty cool, actually. So right now I'm talking about spiral galaxies where it's more simple to interpret it. I'll talk about mess in a little bit. All right, so that is, right there, was one of the first pieces of evidence. All right, so why do objects close to the center of the galaxy move much slower? And the reason is because there's actually not that much stuff, relatively speaking, at the center of the galaxy. Now, it's a little perverse because the center of the galaxy is denser than everywhere else, but it's not like the solar system where all the mass is right at the center. And yes, there is a supermassive black hole right at the center of the galaxy. So the orbits, actually, if you look at the very center, within a few hundred light years of the center, and by the way, the kind of scale we're talking about from here to here is like 30,000 light years. So you're not going to see a few hundred on this plot. If you look at a few hundred, there's going to be a huge spike. Things are moving really quickly because of all the mass right at the center. But once you get outside the inner few hundred or the inner 1,000 light years, there's just not all that much stuff there. Stuff in the galaxy tends to be more spread out. Galaxies are much more spread out than solar systems. And so since there's not so much mass, if things are going in a fast circle, they're going to move out and not stay that close to the center of the galaxy. Yes, and Rudy's right. It's actually a very mesmerizing screensaver, the galaxy collisions. They don't do it right because they don't have kinematic friction, so they tend to spread the galaxies out into individual stars all over the place. All right, so it's actually not true that the laws pertaining to time are consistent, and when you move at the speed of light, the rules are different. It's